Welcome to the 2023 Earth Science Week webinar series based on our theme, Geoscience, Innovating for Earth and People. Today's webinar is sponsored by the Society of Exploration Geophysicists and features two speakers who are currently working on a Geoscientists Without Borders sponsored project where they are applying innovative geophysical techniques to explore groundwater in two rural villages in Nigeria. Our first speaker is Dr. Joseph Sumeje, an assistant professor at the Ahmadu Bello University in Nigeria. Today, he will speak to us about his work as a project lead, where he is applying his research on the application of geophysical techniques to locate, characterize, and manage groundwater resources to explore groundwater for two rural villages in Nigeria.
Good afternoon, ladies and gentlemen. My name is Joseph Sumeje. I am the principal investigator on this GWB project. The topic of discussion is groundwater potential evaluation based on geophysical and remote sensing techniques, providing safe drinking waters to two communities. It is an honor to be here today to discuss this topic that holds an immense importance for community well-being and sustainable development. In this presentation, we will talk about the innovative approach of evaluating groundwater potential using a combination of geophysical and remote sensing techniques. Our focus will be on how this method will be applied to ensure safe drinking water supply to these two communities in northern Nigeria. The community problems. Access to safe drinking water is a fundamental human right and a key determinant of public health. These two communities we are addressing here have been grappling with limited access to clean and safe drinking water due to the region's arid climate, population growth, and dwindling water resources. Residents of these villages use open hand-dug wells that are often polluted. To make matters worse, during the dry seasons, even these waters are not available. This has led to several health concerns, economic challenges, lost time for school children and housewives, and overall hindering community development. Groundwater has been a resource that is hidden beneath the Earth's subsurface, and these resources hold tremendous potential to bridge these gaps. These two projects are located in Nigeria, Kaduna State, and under the Sabongari local government area. They are a few kilometers from the Ahmadu Bello University and the Nigerian College of Aviation and Training Institute. These two project locations are known for their complex hydrogeological settings with varying subsurface structures and unpredictable aquifer characteristics. The two villages have a population of over 20,000 inhabitants who have suffered extreme water scarcity, especially during the dry seasons. Numerous hours are spent sourcing unhealthy water for domestic use, and this has become an annual ritual. Children and women bear the main responsibility for water sourcing, with little or no time for other meaningful activities, like working towards contributing to family's income or receiving education. Groundwater mapping is the foundation for any successful water resources management strategy. It involves the use of remote sensing, geological, hydrogeological, and geophysical techniques to understand the surface and subsurface characteristics like the aquifer formations and recharge sources. Accurate map aids in identifying potential groundwater sources and guide efficient drilling efforts. Our approach in these projects combines the remote sensing data and the geophysical technique, specifically the vertical electrical sounding using the Schlumberger array. This integrated approach enhances the accuracy of groundwater mapping that can pinpoint potential aquifer, determine depth, and identify areas of good water recharge. First, we started with the remote sensing using the Landsat 9 satellite data and processed this data using the GIS tools to create the land use land cover map, the drainage pattern map, the slope map, and the linear density map. These maps were then combined to generate a potential groundwater map of the region shown. And the results shows that the two communities where these projects are cited fell within the moderate to fair classification of the groundwater potential. With this knowledge of the nature of the groundwater potential of these two villages, we were forced to create a work plan that will help us further achieve the aim and objectives of this project. We started with the community awareness and engagement, and we realized that empowering local communities with knowledge about groundwater mapping and exploration is essential for a long-term successful project. Therefore, we engage the community members in the process to foster a sense of ownership, which is crucial for maintaining and managing groundwater resources responsibly. After the sensitization, the local residents were involved in identifying areas of concern and potential well locations. They provided securities for the project participants in some hostile locations and securities for the equipment on field. Their input has ensured that groundwater potential assessment was tailored towards their community's unique need. Then we continued with the geological survey, which includes the mapping of rock types and rock outcrops. These surveys were done with the locals and the students who were fully involved. And this led to the creation of a geologic map for the two villages. And the geological map for the Angwan Fulani shows a predominantly single rock type, which is underlain by a quartz porphyritic granite with one or two outcrops around the study area. Whereas the Angwan Rimi has basically two rock types, the quartz to medium grain granites and the granitic gneisses. We then continued with the geophysical mapping and survey, thereby identifying locations where VES measurements can be carried out in each village. Several VES measurements were conducted around each of the villages to determine the geological layers and its variation with depth. The processed VES results. We used the Dzurak formulation to obtain the hydrological parameters of conductivity and transmittivity. A transmittivity map was plotted for each village And this was used to identify the potential groundwater bearing formation that will produce a good yield of water. According to Newa's and Sangel's classification of transmittivity's magnitude, Angwanfulani falls within the transmittivity range of 100 to 1000 meters square per day, and hence implies that the aquifer has the capacity to supply groundwater for the whole community's consumption. While the Angwanrimi falls within the transmittivity range of 1 to 10 meters square per day, and hence implies that the aquifer has the capacity to supply groundwater for private consumption. Guided by these results and information, we selected a point to drill, and the selected points for 2 villages yielded a positive drill. Water samples from each village went into the multi-user laboratory of the Medbello University for analysis, and a water quality test was carried out, and an appropriate filter was added to improve the water for public and domestic use in each village. According to the results, the water quality index for 20 parameters of the Angwanrimi Basawa is 2782.594, while the water quality index for 20 parameters of the Angwan Fulani is 1756.366. These two values of the water quality index obtained shows that the groundwater location is within the suitability for drinking range as designated by the water quality index ratings modified after Tiwari and Mishra 1985, House and Ellis 1987, CCME 2005, and Yongu et al. 2022. Since this project is a multidisciplinary project involving the engineering, the ironwork construction was handled by the engineers, the mechanical engineers, and the civil engineers. And the engineering aspect started with the ironwork. The students were trained with the locals through each stage of cutting, filing, welding, and then coupling for each site. An overhead tank structure was erected to carry the water tank and also to hold the solar panel that will power the submersible pump. The installation of the submersible pump and the solar panel were all done with the students and the locals on site. The plumbing, and the testing, and the water stations were all completed and checked for any problem. The success of this project, apart from providing clean and safe water for these communities, we have also conducted a training session to build the capacity of the community members to operate and maintain the water station facilities in such a way that hygiene is always practiced. Repair and replacement of damaged parts are done effectively. Changing of filters and cleaning of filter vessels are handled properly by the trainee. Also, the water station facility and its environment have always attracted the inhabitants of these villages every evening, where they gather together to chat and dialogue and discuss their experiences during the day. From our few verbal reports gotten from each site, specifically the Angwan Fulani, a local has reported that the improved water has reduced the frequent sicknesses experienced by the little children in the community. And then school children now resume school early because of the close proximity of the water facility. Challenges experienced at the beginning of this project. When we were carrying out the geophysical survey, we were faced with mild hostility by some villagers who were angry and revolting about this project, believing it was another empty political campaign. This was coming at a period where the country was preparing for an election in February and March of this year, 2023. However, we were able to convince them going through their village heads and some community members. Also, due to poor town planning, it was difficult for us to be able to carry out more VES measurements because of insufficient space for VES profile lines. And also, after delineating the region for the best groundwater yield, we were faced with the choice of selecting a spot that is best to drill, such that it will be easily accessible, easily maintained, and easily secured. The lesson learned from this project, we were excited that the integration of subsurface investigation techniques can yield a perfect result that can solve a community's problem. And also, geophysical field experiences can help students and locals develop the desire to build career in geophysics. The sustainability of this project. Both villages have shown their commitment to secure and maintain the water station facility. As a result of this, we have also trained from each village, a local who is experienced in plumbing and electrical. That will be the first point of call should any sudden breakdown or minor malfunction occurs. In fact, in one of the village, which is the Angwan Rimi, the village head has set up a monitoring and maintenance committee that will be responsible for the supervision of the water facility. While in the other village, a vigilante security post was created to secure the water facility at all times. This project was commissioned on the 16th of September 2023 by the Vice Chancellor of Ahmadu Bello University, Professor Kabiru Bala. Ahmadu Bello University is the host university of this Geoscientists Without Border project.
I commissioned this water project, which was fully sponsored by Scientists Without Borders under the aegis of the Society of Exploration Geophysicists. And we hereby commission in the name of God.
Thank you very much. Yes.
In conclusion, this project has shown that integration of geophysical and remote sensing technique has proven to be a valuable tool in assessing groundwater potential and enabling the supply of safe drinking water to both communities facing water scarcity. This approach ensures that the communities have a reliable and lasting source of safe drinking water. This Geoscientists Without Border project has not only addressed immediate water needs, but also contributed to long-term community well-being, improved health, sustainable water resources management, and human development. In general, the success of this project was due to my entire team's cooperation and the students and the local participants, and also to my project partners. This project's aim and objective has been fully achieved in both villages. And I can say that the sustainability of this project is built in the work plan via knowledge transfer and training and capacity building for the two communities. I wish to acknowledge and appreciate the Geoscientists Without Border under the umbrella of the Society of Exploration Geophysicists for sponsoring this project and giving me and my team the opportunity to execute and fully deliver this project. I also wish to thank and appreciate the host university of this GWB project, Ahmadu Bello University, and all its management for supporting and assisting me towards achieving my aims and goal in this project. I also wish to appreciate the organizers and moderators of this Earth Science Week webinar 2023 under the umbrella of the American Geosciences Institute. Thank you for your attention, and I'll be delighted to take any question you may have on this discussion.
Thank you, Dr. Osameje, for sharing how innovative technologies are helping to locate groundwater sources. Our next speaker, Daniel Ishi Miyake, will now speak about his role in the groundwater project from his perspective as a scholar pursuing a PhD in applied geophysics at Ahmadu Bello University.
Hello everyone, thank you for joining me today as I talk about locating water resources for rural communities, a case study of the Geophysics Without Borders project at Angwan Fulani and Basawa communities in northwest Nigeria. This talk will be centered on the view as a student who was involved throughout the execution of the project. To start, I want to thank Geophysics Without Borders and Ahmadu Bello University for the support of the project and the avenue created for students to participate in the project. In this presentation, we will be walking through a few steps to locate water resource, and they include assessment of water needs, geophysical survey, infrastructure assessment and implementation, and finally capacity building. Assessing the water needs of the communities involved. This project began by conducting a thorough assessment of the specific needs and priorities of both communities, which are the Angwan Fulani and Paladan community. Now, understanding the population size, water demand, and existing water sources were the key priorities looked upon. It was discovered that no potable water source was available in both communities. We also looked at their agriculture and livestock management style and also found out that they had no quality water resource to boost their agricultural demands. So we involved the community leaders in the decision-making process, where we were able to gather insights and traditional knowledge about such water sources. Now, having established the water challenge facing both communities, we conducted a geological and hydrogeological studies to assess the feasibility and sustainability of groundwater in both areas. Now, this involved analyzing the geology of the area, water table levels, and aquifer characteristics. The next phase in locating water resource was to carry out a geophysical survey. Here, the choice of geophysical method was the electrical resistivity technique, and the choice was based on its non-invasive nature and its ability to create a spatial subsoil model without the use of heavy equipment. So there are basically two main types of electrical resistivity survey. Number one, we have the vertical electrical sounding, and its principle is based on the fact that it collects resistivity data at different depths beneath a location. And the next was the electrical imaging, and it works by determining the subsurface resistivity distribution across a profile. It is also being applied for water prospection, mineral exploration, and archaeological studies. For this project, we employed the vertical electrical sound, and the slow measure array was used as the array technique. A total of 48 vertical electrical sounding points were taken, and these pictures depict how the students were put through in the data collection. The students were taught the principle behind the electrical resistivity sounding and how data is being collected, and also how the equipment is being operated. The next phase was the infrastructure assessment and implementation. Here, the infrastructure needed to assess and distribute water from the chosen source was determined. Now, this involved constructing overhead tanks, stands, drainage system, and distribution channels. Now, these pictures depict the involvement of students in the fabrication and construction of the overhead stand. After the fabrication, a suitable location was chosen to set up the water station, and there are factors that were considered, and such factors included the accessibility to the community and the security of the facility. As can be seen, the students were fully involved in the installation process. After a successful installation of the infrastructure, building capacity of the local community was then carried out. And this involved training some of the local community members in the operation and maintenance of the water infrastructure. And this is because training and knowledge transfer are essential for long-term sustainability. Finally, I would like to point out the benefits of this project to the students involved. A few important benefits include interdisciplinary learning. Now, this project involved students from various fields of study, which include engineering, geoscience, geology, physics, and science education. The project created a harmony, and the students discovered how they could contribute to geoscience regardless of their discipline of study. Hands-on field experience. The project allowed students to work outdoors, and they were able to gain practical experience in data collection, instrumentation, and geological observation. Also, career opportunities. This project showcased various career opportunities to the students. The students now see exactly how they could contribute to society through groundwater exploration and geoscience as a whole. And then finally, intellectual growth. The project challenged the students to think critically and creativity, and especially during the physical survey, the geophysical survey, and fabrication of the infrastructures. They showed their resilience and showed their brilliance in making the project a success. So this project was able to showcase and empower female students who can contribute to greater gender diversity in science, technology, engineering, and mathematics. Their presence and achievements can inspire future generations of women to pursue STEM careers in Nigeria and Africa at large. Thank you, and I also want to say a big thank you again to Geophysics Without Borders and Ahmadu Bello University for the opportunity to be part of this project. If you have any questions, feel free to contact me.
Thank you, Daniel, for sharing the steps of this successful project and the work being done by Geoscientists Without Borders to ensure access to safe water sources for all. My name is Lindsay Mosa, and as an education specialist with the American Geosciences Institute, I want to help relate the work of geoscientists to the classroom and how to use sustainability as a way to discuss their work with students. The overall mission of GWB is to apply the geosciences in a way that helps to address the needs of humans around the world. GWB has many ongoing projects that address issues that can be resolved by the application of geophysics. As shown on the map, these projects are related to many geoscience-related hazards, such as earthquakes and volcanic eruptions, as well as processes that connect human activity to geoscience, such as pollution and water quality. As discussed today, the projects occurring in Nigeria are directly tied to water quality and locating water sources that are safe for human consumption. As Geoscientists Without Borders design their projects, they specifically align them to the United Nations Sustainable Development Goals. There are 17 SDGs that address the major challenges faced by humanity today. The SDGs address social, economic, educational, and scientific challenges, among others. Each SDG is broken down into targets and indicators which describe actions that need to be taken to address these challenges. As you read through the tiles, consider how many of them can be directly related to work being done in the geosciences. For example, zero hunger can be tied to the work of soil scientists who are helping to improve crop growth, leading to an increase in food production that can help to sustain human populations. The work discussed in today's presentations were designed to help address three specific SDGs. SDG 3, Good Health and Well-Being, SDG 5, Gender Inequality, and SDG 6, Clean Water and Sanitation. The work being done by GWB can be discussed in classrooms, especially in relation to the SDGs, to bring a real-world context to earth science concepts. The underlying geoscience principle of the project presented today is the location of sources of water that are safe for humans to consume. SDG 6 has the goal of ensuring access to safe water sources and sanitation for all. As described in today's presentations, the work of geophysicists can help to locate aquifers that can provide water for populations that have not previously had access to their own water sources. Within SDG 6 is Target 6.1, which calls for equitable access to safe and affordable water sources. The work being done in Nigeria to locate water sources will ensure that populations are able to not only access but manage water withdrawals, so these communities do not have to travel long distances to access water. Introducing topics from the lens of Sustainable Development Goals can help students see the connection between geoscience concepts and their lives or the lives of others. These projects can also help students understand how engineering concepts and practices are being used to address problems beyond the scope of the geosciences. For example, SDG 3 is working toward ensuring healthy lives for everyone. Target 3.3 has a goal of reducing occurrences of epidemics, including those caused by waterborne pathogens, while Target 3.9 looks at reducing exposure to contaminated water sources, whether it be during consumption or hygiene practices. Both of these goals can be achieved by locating water sources that have not been affected by pathogens or sources of pollution, as is being done in the GWB project in Nigeria. SDG 5 has the goal of achieving gender equality, focusing on the roles of women and girls in their communities. Target 5.4 relates to GWB's water project in Nigeria, as a lack of access to clean water and sanitation facilities directly affects women's health. Also, in many nations, the role of collecting water falls to women. Locating safe water sources can reduce the workload and health risks of women around the world. We hope now that you can see how GWB projects and the SDGs can be used to show students many different problems that can be addressed by the work of geoscientists. These projects are also a way to directly discuss careers within the geosciences, the education and skills needed to obtain and do these jobs, and the work they can accomplish to improve the quality of life for populations around the world. Please visit GWB's website to see more information on the water project being done in Nigeria and other projects being done around the world. For more information on the SDGs, including the graphics seen in today's presentation, visit sdgs.un.org. Thank you so much for your attention to today's webinar and the presentations on the important work being done by Geoscientists Without Borders to ensure access to safe water sources. We'd like to especially thank the Society of Exploration Geophysicists for generously supporting this webinar. We have today's speakers here with us now for a live question and answer session. Please let us know any questions you have by typing them into the chat. To get us started, I wanted to ask Joseph, will you please elaborate on your experiences in working with community members during this project?
Thank you, Linley. My experience had been wonderful because you come in contact with people that are not learned, and you have to explain things to them in the way that they will understand. For instance, in the field, when we were carrying out a geophysical survey using the electrical resistivity method, they were so curious about what we're actually doing, burying electrodes on the ground. And I try as much as possible to explain to them, like, what are we really doing? And I had to tell them that we are trying to snap or take a snapshot of the picture of the Earth. And that was as much as possible as I could explain to them in their lay term to be able to understand actually what we were doing. Most of them are good and interesting people to work with. They are so much inquisitive about learning how we could probe the Earth to know exactly where water can be located or sited. And so I've really had a wonderful experience working with the villagers around there.
Thanks so much, Joseph. This is Lauren. I'm also an education specialist with American Geosciences Institute. Just thank you and Daniel so much for your presentations. I'm going to get us to the first question in the chat. It's, what is the depth of the wells in the two villages?
In each of the village, we were able to drill up to about 70 meters for each.
Great, thank you. As a follow-up to that, we saw in the geologic map the areas that were selected for wells was coarse material. For all of our students that are tuning in today, will you explain why coarse material is a good location for a well?
Hello, please come again.
Oh, yep, sorry. So during the presentation, you showed a geologic map about the locations where the wells were drilled, and it was made up of a lot of coarse material. Can you explain why a site like that is a good spot for drilling a well?
I'm having a little challenge with my network, but if I get your question properly, you said I should explain why the wells were sited in a quartz,
yes,
the granitic.
Yep, that's correct.
Okay. From our measurements, from the VES measurements, we notice that the depth to weathered, the depth of the weathered basements are actually thicker than we expected in some locations. And when we plotted the contour using the generated transmittivity values, we were able to narrow down to a specific region where we feel we could get a good yield from the analysis that we got. And that was what gave us an idea and the confidence to actually start the drill in those locations.
Okay, thank you. And a follow-up that's related to that, what informed your selection of sounding points for VES?
VES had been a well-established array type that could actually probe deeper for water exploration. And based on the formula that we want to use, the Zaruk parameter, we have to get the geoelectric layers of the region. And so the vertical electrical sounding was going to give us a better depth probe and a geoelectric layer, section for for around the study area. And so that was what prompted us to the choice of vertical electrical sounding, because we believe it's actually going to probe deep, and we needed a good depth to be able to carry out or plot a spatial distribution for our water quality probe. I don't know if I've answered your question.
I think so. We'll move on to the next one. The next question is, what was the total cost and time frame of the project? Was all of this funded by GWB, or were there also other sources?
Okay. The total cost of the project is about $53,000. I'm not sure of the extra, but it's about $53,000. And out of these, the Geoscientists Without Border contributed $48,900 out of which. We had some shared costs which were borne by the partners of this project, like the Science Tech is a geophysical company that rents out equipment and the rest. And then the multi-user laboratory that we used in Ahmadu Bello University granted us some waivers in the cost for water quality test and analysis. I think those were the little waiver that we got. The actual cost of the project is about $53,000. The duration of the project is actually 1 year, and I was so fortunate to deliver the project in the 1 year because we had a lot of challenges to start the project, which was from last year September. The universities were on strike, students were not available, and it was not wise for me to go to the field without them, because they are supposed to be fully involved in the whole project. And so it was really difficult for us to start. This year, we had an election, the country this year, and a lot of activities were put on hold until after the elections before we could continue with our field work and measurements.
Great, thank you so much. We had another question in the chat about the possibility of using drones in your work. Do you use any drones while you are doing this work in Nigeria?
No, we didn't have the resources or fund to use drones.
Great. I'll have address a couple of comments in the chat. We have basically 2 participants who have asked if it would be possible to see an electrical tomography profile to get an idea about the aquifer geometry. Is this something that they can email you about and you can share with them, or can you give us some more information about what they're asking for?
Okay. Electrical resistivity imaging is an image of a profile line along where you take your measurements. In this work, we're not really focused on using the electrical resistivity method, because we had to use the Dalzaruk formulation, which is just a computation of the transmittivity values which you obtain from the vertical electrical sounding, the VES. You get the parameter of the suspected aquifer thickness and then the resistivity of the aquifer layer. That is what you use in your formula to calculate your horizontal transmittivity and conductivity, from which you use your transmittivity to plot a spatial distribution of the study area.
And related to that, what is the effective depth of investigation of the electrical survey?
We were able to probe for each VES, we're able to probe up to 100 meters.
And a question in the chat was, when we are drilling boreholes, how do you decide the well and the depth of the well? And I'm assuming some of the methods you've discussed go into that decision, but you want to elaborate a little bit more as well?
Okay. Okay, from our VES points around, we realized that for depths of beyond 65 to beyond 65 meters, the resistivity values were quite very high. And we believe with those resistivity values, we have gotten to the fresh basements, which are not promising for water reservoirs aquifer. And so the best decision we took after analyzing the whole result was to drill as far as 70 and then stop.
And another question from the chat is that in the US, we would do a similar pump test. Was a pump test done for these wells?
Yes, we did pump tests for each of the wells. And we were able to get a pump rate of about, okay, we were able to get a pump rate of about, I can't figure out, I can't remember the exact value, but we were able to do a pump test for each of the wells.
Great. And if that person wants to email us the question at the end, we can forward it on to our speakers to get the specific information if they're still interested in the exact values. The next question in the chat was, if I'm not using a VES or electrical resistivity, how do you know the site of drilling?
Hello, come again, please.
If I don't use the VES or electrical resistivity, how do you know the site of drilling?
Well, you have to carry out a geophysical survey. If you're not using the VES or electrical resistivity a method, you have to carry out other geophysical method to be able to know a location to drill. If I get your question right, I think you have to carry out a geophysical survey to get a location to drill.
I do believe that addresses the question. So, but they can always ask a follow-up just in case. But another question about the VES is that it has a technical limit related to geological complexity and other factors. This person would like to get an idea of which technical problems you encountered during the acquisition and geoelectrical model interpretation.
Okay. At first, we had some limitations in the field, which is, if you observe from the displayed results, the VES points were not properly distributed around the study area. One was as a result of limitation to space. And so our distribution of the VES point was not very dense. During the interpretation process, you could encounter problems if you are not exactly sure of what iteration number to stop during your inversion process, because you have to carry out an inversion process for the VES measurement to be able to get your displayed parameters for the depth and thickness of each of the layers. And so if you are not careful about your iteration process, it becomes very difficult for you to be able to stop at a good point.
Great, thank you. Our next participant asks, do you have any additional locations where you can do similar projects?
Hello?
Yep. And our next person asks, do you have any additional locations where you can do similar projects?
Yes. We have a lot of interest in this work, particularly from around who were fortunate to be around when we are carrying out the drilling, especially. Other communities around are equally eager to see such a project be sited in their locations. And because water scarcity is a serious problem in some part of northern Nigeria, and resources are very limited to actually drill everywhere. And it won't be wise to drill everywhere because we'll have to think of water quality, management of the groundwater resources. And so there are other villages around that are actually looking forward to this, to such kind of project being cited in their communities. So I think there are a lot.
Okay, thank you. We had a follow-up about VES. What is the tolerance of the geoelectrical models compared with the drilling wells?
Okay. We had a good correlation with our geoelectrical model, because from the samples of rock that we received, they were very much in good correlation with what we anticipated from the geoelectrical sessions.
Great. Our next question, in the study locations, is there any contamination issue or potential concern of wells water caused by human activity?
I can say from surface, maybe surface drainage waters. There's possibility that there could be contamination, but from our water quality tests that we carried out, we have not noticed or observed any such contamination. But maybe with time, maybe as a result of their pitch latrine system, which some of the villagers still use, there could be possibility of seepage into the parts where the well had been located. But I think that will really take a long process, because during the construction of the wells, we were able to create a casing to a certain depth to be able to contain such shallow contamination from getting into the water.
Thank you. And how big is the population that these water projects serve?
The population is actually big. I can say that, to the best of my knowledge, just like the chief of the village spoke during the commissioning project, where he said that he seriously believed that there are over 30,000 persons, up to 50,000 persons that can benefit from this well. And I become scared because for you to have just one source of water might become too, let me say, too short to be able to serve this kind of population. But I believe that with the siting at this location, we have a good yield that would go a long way in meeting their needs for now.
Great. And our next question from the chat is asking about the tolerance of the geoelectrical models compared with the drilling wells, and following up asking if the aquifer is carbonates or clastics.
If I may understand what you mean, the aquifer is actually in the basement terrain, and so I can say that, and the source of water is actually in a good quantity. So I can say that the aquifer is cognate.
Okay, thank you. And did you have the wireline logging data that represents a useful material to investigate the aquifer, the water quality, and mainly the establishment of the casing completion profile?
No, I don't have a well log because we didn't carry out such measurements to show to show the log, the well log profile. We didn't have the equipment to be able to carry out such kind of measurement in the field.
Great, thanks, Joseph. And our final question in the chat is, are there plans to install additional wells in the region?
Well, if we could secure more resource and more grants, we hope to actually install more wells in the location to actually reach out to more persons that are in serious need. So yes, we plan to. Thank you.
So if you have any questions that were not addressed, please email us at webinars@americangeosciences.org, and we'll make sure to send you your questions along to the speakers. And we'll be posting the recording of today's webinar on our webinar webpage on our YouTube channel within a week, and we will notify you once the recording is available. Lastly, we wanted to share with you the upcoming webinars in this series. Next up, we have a webinar on the use of drones in the geosciences, in which speakers will discuss applications of drones and their use in earth science classrooms. We hope to see you all at this week's webinars, and that you can check out our website for other ways to engage in Earth Science Week events. Thank you so much for attending today's talk, and thank you again to today's speakers.
Thank you.